Polyprotic acids. Let's take a look at this set of bad boys. Polyprotic acids, by definition, are acidic substances that have more than one proton available to be given up. So molecules like chromic acid, phosphoric acid, sulfuric acid, sulfurous acid, oxalic acid, carbonic acid, etc., they can actually donate more than one proton. And so there is something interesting about the calculations for the pH of such species. All right, now we're basically going to apply the same rules that we have applied to the monoprotic acids or bases. You're going to have multiple equivalence points. Specifically, for every H that's acidic in your compound, you're going to have one equivalence point present in your titration curve. All right, so let's look at phosphoric acid for the sake of giving you a proper thorough example. All right, so, and I'm going to abbreviate the PO4 as A, just to make things simple. But in the first event, phosphoric acid can give away a proton to form dihydrogen phosphate. That has a Ka value associated with it. Since it's the first proton coming off, this is known as the Ka1. And the pKa value for that Ka1, so pKa1 is 2.15. Dihydrogen phosphate can still give away another proton to form hydrogen phosphate. That particular event has a Ka value of 6.3 times 10 to the negative 8, or a pKa2 of 7.20. And the one thing to be noticed right here is that going from the first Ka value to the second one, we have a drastic drop in the magnitude, right? And the reason why is because you're trying to remove an H plus no longer from a neutral species, but you're trying to remove an H plus from something that already has a negative charge. That's going to be a lot harder to do than with the neutral species. And then the last one, where you have a 2 minus charge, hydrogen phosphate can give away that last proton and form phosphate itself. And this process is even more difficult to carry out. Notice that the Ka value associated with this is even smaller, a lot smaller than the second one. So now we have a pK of 12.35. All right, if you actually have solutions of high enough concentration for the sodium hydroxide, you could actually hit each one of the equivalence points for the titration of phosphoric acid. And pretty much what you can see right here is that you have basically like three titration curves kind of like built on top of each other. The first one for the first proton is the one that I'm showing right here. The second one is literally this one right here, and the third one is this one over there at the very end. So we have three equivalence points. We have the first equivalence point here, which is the first inflection point of the graph. This is the second equivalence point, and that's the third equivalence point. And whatever the volume is that requires you to get to the first equivalence point, the second equivalence point is going to happen specifically at twice that amount of volume. And the third equivalence point will happen at 3 times the original equivalence point volume. All right, and that's simply because the number of moles remain the same proportionally. Okay, so if you have 1 mole of acid, you're going to have to titrate away 1 mole of H plus for every single equivalence point, hence the fact that these are going in equal multiples. All right, then you also have the mid equivalence points, which are the volumes specifically of half the value of the ones that you see right here. So if you divide the first equivalence volume by 2, you will get the half equivalence volume. If you divide not 2 times the equivalence volume, but rather the difference, right? The difference right here is the fact that you're going to be adding another half equivalent to the first equivalence volume. So now this is 1.5, and the next one will be 2.5 times the equivalence volume that you had from the beginning, right? So all the values that you see here are in reference to the first equivalence point volume. All right, now this is the attribute that we're going to use to simplify the process, because right now it may look really ugly. It may look like you have to do a humongous number of calculations, but what you're going to see right now is a simplification that is so elegant and so cool that you're going to actually, after you see what I'm about to do, you're going to really want to have this type of problems in your exams, because this will be, ironically enough, the easier ones to perform. All right, so this is how it goes. At the first equivalent point, you're going to have some pH associated with it. But at the first equivalence point, half the value of that volume, you're going to reach the first half midpoint. And at the midpoint, you're going to have a pH equaling to the pKa of the first event. So the pH at the first midpoint is equal to pKa1. Likewise, the pH at the second midpoint is going to equal pKa2. And the pH at the third midpoint is going to equal pKa3. That's just by definition, because we know that the amount of conjugate acid and conjugate base will equal each other at the midpoint, so they will cancel out, and the pH has to equal the pKa at that particular point based on the Henderson-Hasselbalch equation. All right, but this is the part that is super elegant and super cool and simplifies the process a lot. You've seen how time-consuming the calculations of the equivalence point pH values are. You have to do a lot of stuff. You have to do your mice table. You have to figure out how much amount of product you are generating. You have to switch back to concentration. You have to go from Ka to Kb. You have to set up your new ice table, solve for X, get your POH, and then switch over to pH. It's quite a procedure, but check this out. Because we have multiple midpoints present, and because the volumes in between are basically equidistant, right? We are at half a equivalence volume for the first midpoint, and we're at 1.5 equivalence point volumes for the second one. And of course, the equivalence point follows exactly in between them. Then by default, and using just the regular logic of the symmetry of this curve, you could say that the pH at the first equivalence point has to be the average of the first and the second pKa. And so that oversimplifies the problem completely, because all you have to do is just calculate the pKa for the first and second process, average them out, boom, that's the pH at the first equivalence point. And likewise, the second equivalence point for phosphoric acid is going to be equal to the average value of the second pKa and the third pKa, right? So that gives you that value automatic, and that's beautiful because you get those values almost by doing nothing. In fact, as of now, out of the 6 data points that you see here, you can calculate 5 of them probably in a matter of like a minute or 2. It's that simple. The only one that's a little bit annoying is the last one. The last one, because you don't have a final fourth midpoint, this one you're going to have to do the traditional thing of determining the amount left over, switching over to concentration, changing the Ka to Kb, performing your ice table problem, and then switching over from POH to pH. That last one, you have to do all of that, but everything else, as you can see, is super simple, right? pKa1, pKa2, pKa3, and then the average of pKa1, pKa2 for the first equivalence point, average of pKa2 and pKa3 for the second equivalence point. So it's actually not as bad as it looks. So to solve for all the equilibrium concentrations, you could definitely look at the ice table problem, right? If you look at the first event and you start with a concentration of 0.1 molar phosphoric acid, the initial concentrations of hydronium and H2PO4 are 0. Subtract X from the reactant, add X to both of the products. The equilibrium concentrations will be what you see right here on the third row. Applying this to the Ka value of 7.1 times 10 to the negative 3 x squared divided by 0.1 minus x. Here, the 0.1 divided by 10 to the negative 3 is not going to give you a value greater than 400, so you have to use the quadratic formula, which means that you're going to have to cross multiply by 0.1 minus x, bring everything to the same side, find your b value, your c value, input all of them into the quadratic formula, right? Which I'm basically kind of going fast right here, but the process is still the same. Plug in the value of b. You have negative b plus or minus square root of b squared minus 4ac divided by 2a. And simply simplify this from the inside of the radical all the way to the outside of the big fraction, right? Ultimately, you should find out that the value of x for the first process in the dissociation of phosphoric acid is 0.0233. And if you go and substitute that number into the equilibrium expressions, you're going to find out that the phosphoric acid equilibrium concentration is 0.0767, the hydronium concentration is 0.0233, and the dihydrogen phosphate concentration will be 0.0233. So this actually gets you to the vast majority of the values. Now we're going to jump into the second dissociation, the Ka2. And what we have to keep in mind is that we already have a value for dihydrogen phosphate and a value for hydronium from the previous step. Specifically, a concentration of 0.0233 and a concentration of also 0.0233 for dihydrogen phosphate and hydronium. So when we apply the I stable to the second dissociation, and we have the minus x's and plus x's, ultimately we'll have 0.0233 minus x, and 0.0233 minus x. Setting up the equilibrium expression for the second Ka tells us that 6.3 times 10 to the negative 8 has to equal x times 0.0233 plus x divided by 0.0233 minus x. And what this kind of shows you is that 0.0233 divided by 10 to the negative 8 will indeed be greater than 400. So the plus x and the minus x are actually negligible. And what you have right here is 0.0233 divided by 0.0233, which is simply 1. So the value of x is nothing more than the value of the second Ka. Alright, and if you go back to the table and you plug in those values, 0.0233 plus 10 to the negative 8 is still 0.0233. The only thing that really gets affected and changed is the hydrogen phosphate concentration. But the dihydrogen phosphate and the hydronium concentration haven't changed whatsoever because the value of the second Ka is so small compared to the first that the effect is almost negligible. And if we go further to see what happens to the phosphate concentration, we're going to input the value of 6.3 times 10 to the negative 8 for the hydrogen phosphate concentration. The initial concentration of hydronium is still 0.0233. Phosphate, we have nothing to begin with. So we have the minus x, and plus x, generating a similar picture. Now this is the third event. This is the Ka3 event. So we have 4.5 times 10 to the negative 13 equals to x times 0.0233 minus x, plus x, that should be a plus x, all divided by 6.3 times 10 to the negative 8 minus x. Needless to say, 0.233 divided by 10 to the negative 10 is going to be a lot greater than 400. And 10 to the negative 8 divided by 10 to the negative 13, it's actually a little higher than 400. So you can actually cancel out the plus x and minus x, remove them altogether. And to solve for x, you will have to multiply your 4.5 times 10 to the negative 13 by 6.3 times 10 to the negative 8, press enter, divide by 0.0233 and press enter, and you'll find out the value of x is a ridiculously low number, 10 to the negative 18, right? This is not even femtomolar in concentration. We're talking about atto. This is like in the vicinity of attomolar concentration, way too small. For all intents and purposes, you have no phosphate concentration present in there. That's way too small to even exist at the current pH. But altogether, this will be the equilibrium concentrations: 0.0767 for the phosphoric acid concentration, 0.0233 for the dihydrogen phosphate concentration, 6.3 times 10 to the negative 8 for the hydrogen phosphate concentration, pretty much an insignificant amount of phosphate, and a concentration of hydronium of 0.0233, which ultimately means that the pH has to equal 1.63. So this is the entire premise of how you calculate the equilibrium concentrations, also the whole premise by which you can calculate the pHs at the equivalence point, at the mid-equivalence point for each one of the actual points in the titration curve. So with all this being said, we have finished this entire set of discussions involving titrations, and this is particularly a robust topic. Like I said earlier on a different lecture, titrations by some people's definition is the hardest point in the second semester general chemistry class. And we have a few more topics to cover, and you'll be the judge as to whether this was the hardest portion or not. But like everything else in this class, it takes practice. And for titrations, it's very important that you practice it at least a handful of times before you go into an exam, because It's not at all out of the question that this may seem to make sense right now, but the moment you start doing the problem, you're going to realize that you do not really understand it. And until you get to the third time when you're doing it on your own, it will not click in. I can tell you that from experience because that's literally what happened to me. All right, so the last thing I just want to mention is that yes, the pH at the first midpoint, the second midpoint, and the third midpoint is equal to the corresponding pKa's. The pH at the first equivalence point is the average of pKa1 and pKa2. The pH at the second equivalence point is the average of pKa2 and pKa3. So we have all of those things directly. So this concludes the titration lectures, and we will be moving on to the next topic of equilibria, which will basically have us look into how solids dissolve in water and to what extent. All right, so see you in the next lecture series.